Okay, so here's where we left off in the last segment, is we had a boat moving 2 miles an hour across the river, and the river's flowing at 6 miles an hour, and what we discovered is we could write separate equations called parametric equations that describe that motion of the boat. X is independent and separate from Y. We were able to get these equations together by eliminating the parameter t, eliminating time in hours here, by setting it up this way, and we discovered that the path is a linear path. So this is a linear path. Okay, very clear, beginning algebra level. And each of these equations separately are linear in time, aren't they? Aren't these each linear in time as well? Okay. Now what we want to do is we want to use our calculator to be able to run simulations like this. And what I want to do to just make this a little more exciting for you is I want to put another boat on the river. And I actually wrote a little note down here about what I want to do. No, I don't know if I did or not. Well, let's just do it. Okay. Let's say we've got another boat over here on this side of the river, and let's say it's 20 miles up the river, and it's let's say after 4 hours this thing would have traveled 8 miles. So let's say this is at 8:20 is the starting point for that boat, and let's say it's heading at 4 miles per hour to the left, and let's say 5 miles an hour to the left, make it more exciting, and still with the river flowing. So you can see clearly that this one's going to be traveling down here a little below 45 degrees, right? Everybody agree a little more than 45 degrees downward in a path like this? Okay? So the equations for this boat, this first one, I'm going to put a subscript here. I'm going to call this a pair, x1 and y1 on our equations. And I'm going to come over here for this boat, and I'm going to call this x2 and y2, a separate pair of parametric equations. So this boat now is at traveling distance equals rate times time again, at -5 because it's moving to the left times time, but it initially was already out at +8, wasn't it? At +8 miles way across this big wide river. The y motion of this boat is going to be -6 times time, rate times time again, but it initially started up at +20. So we're going to run a simulation now, a simulation of these two boats moving on the river starting at the same point in time, same time. Okay. We can set this up on the calculator by taking our calculator and putting it in parametric mode. Right here, parametric mode. So we come down on our mode screen and we put the calculator in parametric mode. We then go to y equals, and you're going to see equation sets looking like this. They're blank. Notice your first pair, your second pair, your third pair, and there's another pair down below. So we can do multiple parametric graphs at the same time. So I'm real quickly just going to kick in what we originally had. 2t was that first boat's x, and its y was -6t plus 25. See, the math is not particularly hard, is it? And then the second boat's x was a -5 t plus 8, and its y was -6 times t plus 20. Now, I have to then set, here's my set of equations, and so then what I need to do now is set a viewing window. we have control. When we're in parametric mode, we have control on the time. So let's let this thing run for, several hours. Start at 0 in time, and let's let it run for, say, 5 hours, or 4 hours, because the one boat would get all the way across the river in 4 hours, wouldn't it? 2 miles an hour, be across the 8-mile river. Okay, and let's do a steps here in about every 1/10 of an hour. About a 1/10 of an hour, it should be like every 6 minutes, do a calculation. Right, every 1/10 of an hour, okay? And then vertically, now here's our viewing window. So we need to build a picture of the river that's big enough to capture the whole motion. So X minimum, why don't I just say 0, and X maximum, say, why don't I just say 9, and put tick marks, say, every 2 miles on the river, across the river. And then on Y, well, let's go from, say, -10 to 30, and put tick marks every 5. Y'all excited now? Watch this. Here's the other cool thing. Go back to mode and make sure your calculator down here is not in sequential mode, but put your calculator in simultaneous mode. It will draw, as it works its way across a screen or doing calculations, it will draw everything, all the functions you have at the same time as time passes, so you can watch the simulation happen. I always have the calculator in that simultaneous mode because it makes math a lot more interesting. Everybody with me? Parametric mode, simultaneous plotting, and so now hit graph, and I can hit the enter key to pause this. Here comes the review. Well, that was fast. That was too quick. Okay, I'm going to kill it. So what I'm going to do is I'm going to slow time down. I'm going to make it go half as fast. So I'm going to cut this down to every 3 minutes. How do I, if this is 10 minutes, a 1/10 of an hour, 0.05 would be every 3 minutes, right? 0.05, whoops, 0.05. I paused it. Notice that the boat over on the right side of the river looks like it's going to pass in front of the other boat, right? Yep, it did. Isn't that neat? And now watch what happens when you turn trace on. Notice the way I set the viewing window, low enough that I didn't clobber all the bottom part of my graph, and similarly up here at the top. So when the equations are written, it doesn't clobber the path. So I now turn trace on, and I can pick time. After 1 hour, where are they? Here's this boat. Let's see where the other boat is. Oh, look at that. In 1 hour, that other boat is already past the crossing point. Because it was moving 5 miles an hour, remember? Coming across the river. And back to the first boat. So there's where they are relative to each other. Okay? So after 2 hours, boy, after 2 hours, this guy's already over here on the other side of the river, right? Okay. So I'm getting bored with this one. So what I'm going to do is I'm going to come back here and I'm going to change this equation a little bit. I'm going to slow this boat's movement across the river a little bit to 4 miles an hour. Now I'll go graph. Pause. Ah, a little closer together. Okay. Yeah, okay. Yeah, so you can see, you can play a simulation and you can actually change the time. And notice that when we're at trace, say 1 hour, 1 hour, I'm jumping between points here at 1 hour. And you can actually do the calculation. Oh, and what's wrong down below here? I have R and theta given, polar format, polar coordinate format. So I can change that back to XY by going to format up on your zoom key and put it back in rectangular graphing coordinates and then turn trace on. Now we're in XY. So you can see the position of each boat in their X and Y positions. And then you could calculate the distance between them, couldn't you? Okay. Any questions on that problem? Simple, linear paths, parametric equations. Could you eliminate the parameter for each boat? We did it for the first boat. We could eliminate eliminate the parameter for the second boat, and we'd simply have a description with no time.
And no
Oh.
direction.
But the directions would be there,
Okay.
right? The directions are there, built in
Right.
through that slope, right? If you eliminate the parameter, but there's no information in this equation down here about the time. And that would be obviously pretty important if you were interested in how close those boats came to each other and when. Okay, that's a nice linear introduction to parametric equations. Okay, let's do things more exciting because this is trigonometry, right? Okay, so let's do this, and I'm going to write this up on the board so you can have it in your notes. Let's say, do I have time for another linear one? 1, 2, 3, 4. Yeah, I think so. Here we go, another linear one. Another linear model. We're going to have a race. Okay, we're going to have a race. So we're going to say you're going to travel at 6 feet per second. No, 6 miles per hour, you're jogging. 6 miles per hour. It's a reasonable jogging rate. And I'm going to put this first runner on a track that's labeled up at y=2. So 2 is going to be a constant, and this is distance equals rate times time right here, moving at 6 miles an hour. Little picture to go with it. Here's our y-axis. So up here at 2, here's this runner heading out. Okay. Now here comes runner number 2, but we're going to put that runner on a different track. Let's put that runner on track 3. Let's put him on track. Yeah, let's put him on track 3. So I'm going to make this up higher here. So up here is track 3. Here's 2, here's 3. And this runner is going to be traveling at 8 miles an hour. But this runner is lazy. This runner is going to wait for 6 minutes before this runner starts moving. Yeah, sitting around, stretching or whatever, getting ready for the run. Going to wait for 6 minutes. So there's going to be a time delay, right, before this runner starts. How would I build that time delay in for time here? Don't I want to take some time, running time off of this runner? Okay, 1/10 of an hour, 6 minutes. So time's going to start. We're going to start the clock. This runner takes off, getting a head start, and then this other runner is going to come along and eventually catch up. Runner 1, and this runner has a delay. Here comes runner 2, and eventually this runner is going to catch the other one because this runner is moving faster. Everybody agree? The math is not tough. Josh?
Wouldn't you be saying that the runner's going at 8 miles an hour and he starts 48 minutes behind the other runner?
Why would I want, oh, I could do that, but
Well, the way you've written it, wouldn't you want 8t minus 0.01 or 0.1 instead of 8 times t minus 0.1 or 0.1?
keep in mind, distance, I'm going to tuck it in right here. Distance equals rate times time traveled for runner 2. This runner's time at 0.1 hours, 6 minutes, this runner's time running would be 0 then at 0.1. When time is at 0.1 on our stopwatch at 6 minutes, this runner will have traveled 0 time and 0 distance. Every minute thereafter, this is then going to be that difference. So let's see what happens. Let's build a viewing window that'll show both tracks and see what happens with the runners. Oh, my batteries are low, it says. Better get those fixed. Okay, so runner 1 is on track 2, moving at 6 miles an hour. Runner 2 is on track 3, moving at 8 miles an hour, but with a 6-minute time delay. And then I need to build a viewing window. And so let's let it run for, let's say, we could let it run for, let's let it go, no, let's just leave it at 4 hours, every 3 minutes. And then X is going to represent the distance traveled. So if we go 4 hours, wow, that's a pretty good distance then. 24 miles. So 0 to, say, why don't I put 30, put tick marks every 6 miles on there. And then vertically, -1 to 4, 1, just to lay out the tracks. Got those numbers written down. Ready, set, graph. Whoa, what happened? Oh, I screwed up. I meant to have my X and Y's reversed. I've got them running straight up. Did you notice that? There they go. Okay. I had these things backwards. Okay. Track 2 and track 3. Right? Now are we good? No, still not good. This guy here is track 2, right? Now I'm excited. Ready, set, go. I paused it. Look at that. That top runner was already ahead early on. So let's come back here and let's slow this guy down a little bit. Change this to 7 miles an hour. 6-minute delay. No, I'm sorry. I don't want to keep screwing your notes up. Leave it at 8, but let's give it a, instead of 1/10 of an hour, how about 2/10 of an hour delay? Now here comes the simulation. The runner gets ahead pretty quick, right? Okay. So back to the equations. I'm going to slow them down even more. 4/10 of an hour. Ready, set, graph. Still catches them. Okay. So what you can do then is you can let it run, and then turn trace on. And when you turn trace on, you can now pick time. Like let's say you went to 1 hour, and you can be on the first runner, and then you can jump to the other graph and see that the second runner hasn't caught up yet. See how nice that is? Okay, and then we can let time go a little further. 1.2 hours. Let's go a little further. Oh, look at that. Look at the distances. This first runner is still ahead, right? Let's go a little further in time. Whoa, getting close. Isn't this fun? Okay, you can neglect your homework by doing this sort of thing. Okay. Enough of that. Let's get off of linear and go nonlinear. Okay. We're going to have everybody spinning around here in just a second. Okay. This is a trig class, by the way, and we didn't have any trig in those last two problems, did we? Okay. Let's try this. X equals 3 cosine t. What's the range of x possible here? What's the range of x? Good. 3 to -3, right? -3 to 3. The range of x, back in the very first chapter of trigonometry, you can look at this thing, cosine can't exceed 1 or negative 1. So this range on x has to be trapped between negative 3 and 3. So imagine your viewing window, negative 3 to 3. Let's say y is 3 sine of t. That means y is not going to go any more than negative 3 to 3. Everybody feel good? Can we eliminate the parameter here? Can we eliminate the parameter? It's going to get sticky if you go trying to solve for t and you're going to have an inverse cosine, right? To solve that for t. And then trying to substitute that into this other equation, that sounds kind of nasty, right? So there's a trick that you can use on some of these, such as this one. Eliminate the parameter. You know that sine squared of t plus cos squared of t equals 1. We love this thing. So if you take and put the sine reading, which is y over 3 in there, and square it, and put x over 3 in for your cosine, and square it, that's equal to 1. And look at what you get. X squared plus y squared, multiply both sides by 9, equals 9. What shape is it? A circle. A circle. With r equal to 3. Pretty slick. How will the calculator draw it? In parametric mode. Because this thing is not a function, is it? This is not a function, is it? Doesn't pass a vertical line test. So how's it going to draw it if you start your parameter at t equals 0? And let t range from 0 up to 2 pi. Simple trigonometry, right? Which way is it going to go, Joshua?
Counterclockwise.
Counterclockwise, starting out here, isn't it? At t equals 0, this point right here would be 3, comma, putting 0 in here, 3, comma, 0. And it's going to generate it that way. And so what you want to do when you do parametric equations is you want to put an arrow on the direction in which it's building, in which it's generated. So with the calculator real quickly, boy, I'm almost dead in the water here. My batteries are low. I can put in 3 cosine t and 3 sine of t. And I can set a window, 0, this t is now what? Not time anymore. T is an angle, like think of theta or something. And so I want to go to 2 pi on it, and let's let it do it every 1/10 of a radian. Make sure I'm in radian mode. And my window again. And now here, these numbers are important. I've done these before with you. Minus 4.7 to 4.71. Negative 3.1 to 3.1. Oops, screwed up there. Negative 3.1 to 3.11. Those 6 numbers right there, folks, are important because that'll give you an undistorted picture. And now I hit graph, and there it comes, a nice, perfect, undistorted unit circle of radius 3. Trying to get that to work. Can you get the video recording to show the screen there? Oh, okay, it's okay over there? Okay, good. All right, got that one? Okay, let's do another one. Real simple adjustment here. Doing okay. Tell you what, let's stop this segment, and then we'll have one more segment. It'll be about 15 so minutes.